Hello and welcome to the Unit 2 Section 1 video on quadratics in vertex form. So before we start talking about quadratics in vertex form specifically, let's just talk a little bit about what a quadratic parent function looks like. Well, we have a quadratic function as a polynomial where the highest power of any variable is 2. Okay, so a quadratic function is a polynomial where the highest power of any variable is 2. Okay, so you can have x squared, but you cannot have x to the third. You cannot have x to the fourth, fifth, sixth, and so on. You also need to have that squared, that x squared polynomial term, because if you don't have the squared term and you just have, say, 3x plus 5, then it's not quadratic, it's linear. So it has to have a power of 2 in it, nothing higher. We can have some that are lower, but that second power term has to be there. The graph of a quadratic function is U-shaped, and it is called a parabola. Now the highest or lowest point on a parabola, that is called the vertex. And the axis of symmetry is a vertical line that divides a parabola into two symmetrical halves passing through the vertex. So now that we've gotten some of the terminology down, let's take a look at what a quadratic parent function looks like. Okay, so let's say that our parent function is f of x equals x squared. That is the equation for a quadratic parent function. Well, if we plug in -3 for x and we square it, then -3 squared becomes 9. It's not -9 because the negative times a negative gives you a positive, so we will end up with a positive value. Likewise, -2 squared will give us 4, -1 squared will give us 1, 0 squared gives us 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. Okay, so that gives us some points to work with as we draw a parent function. Okay, so we can let's start here with the middle, 0, 0. That's going to be our vertex because everything else on the y-axis is higher than that. So this is the lowest point of our graph, which means we're going to have a minimum. Okay, so let's go over and graph 1, 1. So we go over 1, up 1 to get to 1, 1. Let's graph 2, 4, over 2, up 4. And then 3, 9, over 3, up 9. So there's 4, 5, 6, 7, 8, 9. Now if we graph on the other side, you'll notice that we have -1, 1, -2, 4, and then -3, 9, which will be here. And you'll notice that everything reflects along that axis of symmetry. In the parent function, this axis of symmetry happens to be the y-axis. So whatever we have on this side, we can reflect it on the other. Same goes for the 2, 4. We have -2, 4. And then on 3, 9, we have -3, 9. So we have points that kind of go together, which allows us to graph one side a little bit faster than the other, because if you know what happens to one side, then you know what's going to happen to the other because it's going to be symmetrical. And now here's my attempt at drawing the curve through those points. It doesn't look the best, but it kind of gives you an idea that's what the parabola looks like. I actually think that you get a little bit better idea seeing it just from the dots that we've plotted than from my attempt to draw the curve, but there it is. Okay, now that we have the parent function, hopefully you have that drawn for yourself. Let's take a look at some of the key features. Well, this first one I've already filled in for you. A parabola shaped like the letter U is what the function shape looks like. So let's talk about some of these others. All right, so the x-intercept. Well, the x-intercept is at 0, 0 because that's where it crosses the x-axis, and it actually touches the x-axis only at that point. Okay, so the y-intercept is also the same place. It's also at 0, 0. Now the domain for this function is going to be -infinity to +infinity. Because when you look at this graph, we have an arrow on the left, we have an arrow on the right. Even though they look like they're going up, and yes, they are going up, you got to remember a left-hand arrow tells you we're going to negative infinity on the x-axis. A right-hand arrow on your function tells you you're going to positive infinity on the x-axis. Now our range, we're starting from 0, and everything above that is in our function, but there's nothing below it. So we start at 0, and since it is an x and y intercept, happens to be both, then we're going to include it with a bracket. So we have 0 to infinity. Our axis of symmetry is at x equals 0, so that happens to be the y-axis. Our vertex is also at 0, 0. That's where the minimum is. Now we have a positive interval on the right-hand side of our graph and on the left-hand side of our graph, because it's positive everywhere except for one place, and that is at the vertex, because the vertex is 0, 0. And 0 is neither positive or negative. So we have from negative infinity to 0, union with 0 to infinity, because we cannot include 0 since it is not a positive number. Well, it's also not negative, and everywhere else is positive, so we do not have a negative interval. It increases on the right-hand side of the parabola. On the right-hand side, we're going up, so theirs is increasing from 0 to infinity, and then it's decreasing from negative infinity to 0. So we have increasing from 0 to infinity, and we have it decreasing from negative infinity to 0. And then finally our end behavior, as x approaches negative infinity, well, you know on the left-hand side it's going up, so f of x is going to infinity. And then as we look at the other side, as x approaches positive infinity, on the right-hand side, f of x is also going up, so it's going to positive infinity. So now that we've talked about the parent function, let's talk about some of the transformations that can occur. Okay? So let's take a look at a quadratic function with different rates of change, vertices, and opens maybe downward instead of upward. All of those are just simply transformations of the parent function. Now, you may recall back in the last unit that we talked about the transformations of an absolute value function. Well, you'll notice that this setup for a transformation of a quadratic function looks very similar. So really, if you know the absolute value transformations, then you know quadratic transformations, you know how they work, especially when you're presented with a quadratic function that is given in this form. So f of x equals a times the quantity x minus h squared plus k. This is referred to as vertex form of the quadratic equation. This is the first of 3 forms that we will be covering in this unit. And it's vertex form because, as you remember from absolute value, hk gives us the location of the vertex, and x equals h gives us the location of the axis of symmetry. So here we have the format here at the top, and let's talk about all the transformations. Okay, so if we have a horizontal translation to the right, you may remember from absolute value, the rule is h is positive. Okay, now if we have a translation to the left, h is negative. Now that makes sense, but remember, it is going to look different than what we have listed here. Because when h is positive, well, it follows the subtraction operation. So it's going to look negative. So it's going to look like it should go to the left, when in reality it's going to the right. And here's an example of that. If you have f of x equals x minus 3 squared, that minus would make you want to say that it goes to the left, but in reality it goes to the right because the 3 is positive, it just happens to follow a minus sign, as subtraction is the operation in this formula here. I think it's more clearly seen, like we saw with absolute value, that if we show you what it looks like when h is negative, well, if we have x minus negative 3, h here is negative, then a negative minus a negative, so you got a negative and a negative together, that gives you x plus 3 squared. So it looks like it would go to the right, but in reality 3 is in fact negative because it followed that subtraction operation. So you had minus a minus, which makes it look like plus. Translations up and down are a little more straightforward. If k is positive, then you're going up. If k is negative, then it's going down, or it's translating down. We're moving our vertex here in the translations. So an example of positive, you've got f of x equals x squared plus 5. And then in negative, you have f of x equals x squared minus 5, okay? So this k is on the outside of the x squared portion. So whatever follows the square, that is your k. Reflection across the x-axis occurs when a is negative. So you got that a out in front, so when a is negative, then you have a reflection across the x-axis, and it would look like this. F of x equals minus x squared. A reflection across the y-axis occurs when x is negative. Now you have to be careful here because you may say, well, isn't x negative here? Well, remember your order of operations. You're squaring before you have the minus sign, right? So to have a reflection across the y-axis, you would have to make x negative before you square it, and so it would have to be placed inside the parentheses. Then in the vertical stretch, that occurs when a is greater than 1. So f of x equals 2x squared would be an example of that, because a is greater than 1. That's the number preceding your x squared term. And then the vertical compression occurs when a is some number between 0 and 1. So you'd have a fraction like 1/2, 1/4, 1/3. And here's an example where I just simply write 1/2 x squared. So these would be your transformations of a quadratic parent function to give you different types of parabolas, some that are inverted, some that are concave up, some are concave down, some are going to be wider, some are going to be narrower, some are going to be moved to different parts of your coordinate plane. So let's use these rules to see if we can do a few examples. Let's see if we can identify the transformations that occurred to the quadratic parent function in each of these different problems. So let's start off with A. So we have a number out in front, so that means we have a stretch or compression. And since it's greater than 1, then that means we have a stretch. And that stretch is by a factor of 3. So we have a stretch by a factor of 3. Okay? We also have a plus 2 inside the parentheses, and that tells us that it's translated left 2 units. And that's all that's happening to that first one. Let's move on to the second one here. Okay? So in the second one, we have a minus sign out in front. And that minus sign out in front tells us that we have a reflection across the x-axis. Then the minus 4 on the end, it comes after the squared part, so we have a translation up or down, and since it is negative, we're translated down 4 units. For part C, we have a minus 6 inside the parentheses with the x, so that's a translation. And we are translated down. Well, are we translated down? We're actually translated left or right when we're inside. And since it's negative, or at least it appears negative, we're translated right 6 units. Because remember, what we're actually looking at is x minus positive 6. So h itself is positive, which means it's translated right. Now the 2 on the outside, since we have a plus 2, that's a translation up. And that translation up is by 2 units. And then finally, in this last example, we have a couple of things going on. So we've got a negative out in front, so that tells us that it's reflected across the x-axis. We have a 1/3 out in front. Since it's between 0 and 1, that means we are compressed vertically by a factor of 1/2, or I should say 1/3. Then we have a plus 1 inside with the x, so we have a translation to the left 1 unit, because remember it's x minus negative 1, and then we have a translation down by 5 units. And that's everything happening to that last example. So we are able to identify transformations looking at equations. Let's see if we can identify what's happening with a function given the equation. Let's see if we can identify some of the key features and graph it. So let's start off with this first one. Well, the vertex is hk. And remember, h is whatever comes after the minus sign. So we have plus 2 on the inside, which means it's minus negative 2. So our vertex would be negative 2. And then we have a minus 3 on the outside, so it would be negative 3. Our axis of symmetry is just our x value from our vertex, so that would be x equals negative 2. Our y-intercept. To find the y-intercept, you'll need to plug in 0 for x, because remember, along the y-axis, your x value is 0. So if you plug in 0 for x, you get 2 squared, which is 4, and 4 minus 3 is 1. So your y-intercept is 1, y equals 1, or the coordinate pair 0, 1. All right, do we have a maximum or a minimum? Well, there's no minus sign on the front, which means that it's going to be concave up. And when you're concave up, you have a minimum. So we have a minimum at y equals, and it would be your y value from your vertex. And then the domain, well, it's a quadratic function, and I'll go ahead and tell you that the domain for a quadratic function will be negative infinity to positive infinity. And the range, well, we're going concave up, so our minimum point is at y equals negative 3. So that will be the front part of your range, negative 3, and we do include it, to infinity. So it's fairly quick to pick out some of these key features of a function if it's quadratic. So now let's plot the vertex. That's a good place to start here. So it's negative 2, negative 3, so that would be right here. And we know what the y-intercept is, so let's plot that, 0, 1. And thanks to it having an axis of symmetry, we know that if we go 2 on this side of the axis of symmetry, we can go 2 on this side and plot another point. Now, ideally, you would like to have at least 5 points to plot your parabola to adequately graph it. So let's see what other points we can get. Well, we know it's not stretched or compressed. So since it's not stretched or compressed, we can use the setup of our parent function to plot some other points. So you know you've got 1, 1, because 1 squared is 1. So you can do that on this side. You have 2, 4, which takes us to our y-intercept, so that's nice. Then you got 3, 9, so you got 3 over 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can plot a point here, and you can plot a point on the other side as well because of your axis of symmetry, and you can also plot a point over here because of your axis of symmetry. And you're starting to see with the dots that the parabola is starting to take shape. And so the only thing left to do is to attempt to graph through the points of the parabola. Now, you'll notice that I'm struggling to draw that with the pad that I'm trying to draw with. So from this example forward, I'm just going to leave you with the dots there, the points of the parabola. You can sketch the curve much nicer than I can through those points. Now, for those of you who may encounter this on a test where you're going to have to graph a parabola, my suggestion is make those points that you're going to be sketching through pronounced, and then maybe lightly sketch your line through those points. That way, it's easy for the instructor to find that you know where the points go, and you know how to at least plot the points that you're going to use as your guide as you sketch your parabola. All right, let's move on to the next example. So in this one, our vertex would be at positive 1, because we are following the negative sign here. Positive 1, positive 5, that's our k on the outside. Our axis of symmetry is at x equals 1, which is simply our x value of our vertex. The y-intercept, if we put in 0 for x, we get negative 1 squared, which is 1, but you have this minus sign out in front of it, so you end up with negative 1 plus 5 gives you 4. So you'll notice that it's fairly easy when you're plugging in 0 for x to do the math without necessarily having to write down all the steps, although you are more than welcome to show the work for that. All right, for maximum and minimum, since we have a negative sign out in front, then we know it's going to be concave down because it's going to be reflected across the x-axis. So therefore, since it's concave down, you're going to have a top part of the parabola, which means you'll have a max, and that's going to occur at the y value of your vertex. The domain, as always, will be negative infinity to infinity, and our range, since we have a max this time, we're coming from negative infinity and we're going to that maximum of 5. So now let's plot some points. The vertex is at 1, 5, so 1 over, 5 up. So there's our vertex. So since our vertex is here, we're expecting all of our other points to be below it. Our y-intercept is one of those, 0, 4. Now we know we're going to be reflected, but since there's no value after this minus sign out in front, then we know it's going to be a standard form parabola, so we'll reflect at this point first. Then we can just go over 2, down 4, and plot a point here, which we can also do to the other side. We can go over 3 and down 9, so 4, 5, 6, 7, 8, 9. And over on the other side. And then let's see if we can do 4, 16, because 4 squared is 16. So over 4, 3, 4, and then down 16. So this would be 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We don't quite make it to 16. It would have to be one more box beyond that. But that's okay, because we have not just 5, we actually have 7 points that we can use to sketch our parabola. We know that we're approaching the next grid box fairly closely when you get to the bottom of the graph. All right, let's do the next one. Our vertex is 3, negative 4, reading that from our h and k. Our axis of symmetry is at x equals 3. Our y-intercept, if we put in 0 for x, negative 3 squared is 9. And so we end up with 9 halves, because we multiply it by the 1/2 out in front, minus 4. Well, 4 is actually 8 halves. You can rewrite it that way to get a common denominator. So you have 9 halves minus 8 halves, which gives you 1 half. So our y-intercept is at 0, 1 half. We have a minimum. Since it is right side up, it's concave up, we're going to have a minimum at y equals -4. Our domain, as always, is -infinity to positive infinity. And since we have a minimum, we're going to start with that minimum, -4, and our range will go on to infinity. All right, let's talk about graphing this one. The vertex is at 3, -4, so we can go over 3 down to -4, and we can plot our vertex. We know that's going to be our minimum, so everything plotted is going to be above that. But we know it's not a standard form parabola. It's going to be either stretched or compressed because there's a number out in front, and since that number is between 0 and 1, we are going to be vertically compressed, which means it's going to look wider horizontally. Well, how do we handle graphing other points? Because our y-intercept really doesn't do a whole lot for us. We could plot halfway between 0 and 1 for 1 half, but we want to try to plot at where our grid boxes cross, if at all possible. Well, here's how you handle working with a compression. You're going to take this number on the bottom, 2, and you're going to take that 1, 1 that you would start with, and you're going to multiply both of those by 2. So instead of going over 1, up 1, you're going to go over 2, up 2, and you'll plot your point. And then you can reflect that across the axis of symmetry. For the next one, instead of going over 2, up 4, you're going to double both of those. You're going to go over 4, up 8. 1, 2, 3, 4, 5, 6, 7, 8. And you'll plot your point. And you can reflect it on the other side of the axis of symmetry. And that's about all we're going to be able to do, because the next one will go off the graph. So from here, you'll be able to draw your curve. We've got our minimum of 5 points needed to draw our parabola. All right, one last example. We have our vertex on this one at -2, 5. Our axis of symmetry is at x equals -2. Our y-intercept, well, that's going to be at, well, let's see what it's going to be at. If x is 0, then 2 squared is 4. 4 over 4 is 1. And 1 plus 5 is 6. So we're going to have a y-intercept at 0, 6. Now, since this is a positive number out in front, it's going to be concave up, which means we're going to have a minimum. And it will be at the y value of our vertex, y equals 5. Domain, as always, is -infinity to positive infinity. And since we have a minimum, our range is going to be 5 to infinity. So let's start with our vertex, -2, 5, which would be plotted right there. We have a y-intercept at 6, so that gives us something to work off of. And then we also have a compression, since we have the 1/4 out in front. So how do we handle that? Well, we're going to use that 4 on the bottom as our factor. So instead of going over 1, up 1, we're going to go over 4, up 4 for our first point. And that's really all we can do. And we can reflect that as well. So these are the points that you will end up drawing your parabola through. And we have the minimum of 5 needed to do that. Okay, let's move on to another example. Let's say we're given some key features and we want to graph our parabola, our quadratic function, using these key features. Well, let's take a look at what we have. We'll start off with A here. Okay, so we have a minimum value at -4. We have a positive interval from -infinity to 1, union with 5 to infinity, and then we have an increasing interval from 3 to infinity. Okay, well, let's see what all this means. Well, we know the minimum value is at -4. So it's going to be somewhere along here is where our minimum will be. But we don't know what our x-coordinate is off of the minimum value alone. But we also know that it's increasing from 3 to infinity. So if it's increasing from 3 to infinity, what does it have to be doing before we get to 3? Well, it must be decreasing, right? So if it's decreasing before we get to 3 and increasing after 3, then 3 must be our minimum x value. And if it happens at y equals -4, then we have our vertex, which I've just plotted here. Okay, so now let's look at the second piece of information. We're positive from -infinity to 1, and then from 5 to infinity, which means we must be negative in between. If we're negative in between, then at 1 and at 5, we must be crossing the x-axis because we have to go from positive to negative, and then from negative back to positive at 5. So those would be our x-intercepts. We'd have 1 at 1, and then we'd have 1 at 5. All right, well, now we have 3 points that we can use for graphing, but we would like to have at least 5. So let's look at the graph and do a little bit of analysis. Well, we know with a parent function, if it's not stretched or compressed, we can go over 1, up 1, and then over 2, up 4. Well, this one is 2 over from our vertex, so let's see how many up it goes. 1, 2, 3, 4. So we go over 2, up 4, which is what we would find in a standard parabola that's not stretched or compressed. So therefore, we can fill in the blanks here. We can go over 1 and up 1. We can go over 3 and up 9. So there's 4, 9 would be at y equals 5. And we can reflect that across the axis of symmetry. And now we have not only 5, but we have 7 points that we can use to sketch our parabola. All right, let's move on to B here. Again, I'm not going to sketch the line through. I'll let you look at those points and you can do the sketch yourself. My sketch is not going to look very good. So let's go over to B here. The range is y such that y is less than or equal to 0. Well, y is less than or equal to 0 means our top part of our function is going to be at 0, which means we must be concave down, since we're going to be reaching a max somewhere along the x-axis. Well, we're increasing from -infinity to 2, which means we must be decreasing from 2 on. So that gives us the other part that we need for our vertex, which would be 0 or 2, 0, because we have our range topping out at 0. We have no positive interval, which kind of confirms that it's going to be concave down. We'll have nothing happening in the top part of our graph. We have a y-intercept at 0, -8, which is right here. And we can reflect that across our axis of symmetry. So now we have 3 points. Well, let's do a quick analysis. If we go over 2, we're going down 8 instead of 4. Well, this is what happens when you have a stretch. When you have a stretch, you're going to take whatever that factor is, and you are going to stretch the y by that factor, but not the x, okay? So you'll multiply. In our standard parent function, we go over 2 and down 4, since we're inverted. Well, we're going to double that 4 to 8. So we must be stretched by a factor of 2 here. If that's the case, then we can go over 1, down 2, instead of down 1. And that gives us our 5 points to sketch our parabola. Let's do a couple more of these examples. So in this one, we have a maximum value at -4. We have no positive interval, and we have an increasing interval from -infinity to 4. Well, since we're increasing from -infinity to 4, we know that 4 is going to be our x for our vertex, and the maximum is going to be -4, which means this is going to be the top. Let me clean that up just a little bit. Which means this is going to be the top of our parabola. And if that's the top of our parabola, we're going to be inverted. And that's really all the information that we are given. We know that where our vertex is, we know that we are inverted. So from here, my suggestion is, since we're given no other information, that we just go ahead and plot our other points as if this were standard form so that we can graph the rest of the parabola. And so there are the points that you would use to do your sketch. All right, last one here, our range. Y is less than or equal to -1, so we know that we're going to have a maximum of -1. And we're increasing from -infinity to -3. So that means our vertex is going to be -3, -1. We have no positive interval, which confirms that this will be concave down, all below the x-axis. And we have a y-intercept at 0, -10, which we can reflect across our axis of symmetry. Now let's fill in some gaps here. Well, let's see if this is stretched or compressed. Well, if we go over 3 in a standard one that's not stretched or compressed, we would expect to go down 9, which is indeed the case here. So it's not stretched or compressed, so we can fill in over 1, down 1, over 2, down 4. Let me get that a little bit better. And there are the points that you would sketch your parabola through. All right, in this next example, we're going to write an equation for the graph of the given function and then identify its given key features. Okay, so here we're given the graph. Let's identify some things first and then we'll graph our equation, at least for this first one. So our y-intercept, that's going to be at 0, 2. Our vertex is at 2, -2. And our range is from -2 to infinity. All right, so let's see if we can write an equation using some of this information and using what we're looking at on the graph. Well, first of all, it's going to be concave up, so therefore it's going to be positive out in front. And it's not stretched or compressed because we can go over 1, up 1, over 2, up 4. And so it is standard, which means we're just going to start with our x. Well, our vertex tells us what's happening inside with the x. Okay? So we have a positive 2 as our h, so we're going to have x minus 2 squared. And then we're going to have our second part of our vertex, our y-coordinate, telling us how much it's translated down. Since it's translated down, we have -2 out here. And technically, I did forget to write f of x out in front. So let's write that. F of x equals x minus 2, the quantity, x minus 2 squared, minus 2. That's your equation. All right, let's look at B here. Let's start off with the equation. So we know where the vertex is, so we'll use that information. And we know that it is stretched. You can see just by looking at it that it's stretched. Let's see what factor it's stretched by. If we go over 1, we go up 2. So it's stretched by a factor of 2, and we can confirm that. If we go over 2, we should go up 8. 1, 2, 3, 4, 5, 6, 7, 8. Yes, it is stretched by a factor of 2, and it's concave up, which means it's going to be positive. Now, we have the next part. Our vertex is at 0, -3. So that 0 goes inside the parentheses with the x. Well, we don't really have to write that. It would be just x minus 0, which would just be x squared. And then we're down 3, so we're translated down 3. So our equation would be 2x squared minus 3. Our domain, always for quadratics, -infinity to +infinity. In behavior, well, this is also going to be something that you'll commonly see, especially with concave up, as x goes to +infinity. So we're looking at the right-hand side. F of x goes to +infinity. And as x goes to negative infinity, which is the left-hand side, f of x also goes to infinity on that side as well. Now let's do the rate of change, and I'm going to kind of scoot this up a little bit so we have room to do that. Recall that rate of change is change in y over change in x. So all that really means is we're going to do y2 minus y1 over x2 minus x1. Well, our x's are, let's say x2 is 2, x1 is 0. Let's find what our y2 that goes with 2 is. So at x is 2, our y is 5. And then when our x is 0, our y is negative 3. And so we get 5 plus 3, which is 8, over 2. So our rate of change is 4. All right, let's do a couple more of these examples. In part C, we have a parabola that we can very clearly see is compressed, but it's also concave up. So we know that the leading term is going to be positive. It is compressed, so when we have compression, we are going to count over 2. Well, 1 is out because it's not standard. Let's go over 2, up 2, and yes, we do cross there. And then the next one we would expect to be over 4, up 8, and it does look like it's going to be going that way. So we are compressed by a factor of 1/2. So we start with f of x equals 1/2 is the number that'll go out in front. What's going on inside with the x? Well, we've got a vertex of negative 3, 1. So that negative 3 is minus negative 3, which would be plus 3 squared. And then you have plus 1 on the outside for your y translation. Our positive interval is from negative 3 to infinity, but it's also negative 3 to negative infinity, or negative infinity to negative 3. Remember, positive is anything that's above the x-axis. So our positive interval is everywhere. And then our negative interval, since it's positive everywhere, you have no negative interval. Now it's increasing from negative 3 to positive infinity. All right, now to part D. We have an equation here that we want to find. It's going to be some f of x. So let's see what's happening. Well, first of all, it's concave down, which means the leading term will be negative. And we are stretched. Let's see what we're stretched by a factor of. We go over 1, down 1, 2, 3. So we are stretched by a factor of 3. Inside with the x, we go back negative 1 is our x coordinate. So it's going to be x minus negative 1, which is x plus 1. And then up 4, translated up 4, which means we have a plus 4 on the outside here. Our axis of symmetry is x equals negative 1. Our decreasing interval is from negative 1 to infinity. And our rate of change, we're going to do change in y over change in x, which is y2 minus y1 over x2 minus x1. y2 and y1 we'll find after we write down our x2 and x1. So let's make x2 negative 1. And we'll do x1 as minus negative 2. So where x2 is negative 1, our y is 4. And then negative 2, our y is 1. And so we have 3 on the top, negative 1 minus negative 2, which is negative 1 plus 2. That's going to give us 1. And so our rate of change is 3. Okay, let's finish off this section by showing you how to write quadratic functions in vertex form. Okay, so in this case, you're going to be given a couple of pieces of information, and you are going to write the quadratic function using those two pieces of information. So to write a quadratic function in vertex form, first we're going to plug in the vertex for h and k, and then the point for x and y. All that'll be left is a, and that's what we're going to solve for. After you find out what a is, we're going to take the vertex form of the quadratic equation and plug a, h, and k back in without plugging in x and y. So we actually have a general formula for the quadratic. So let's do these three examples to show you what I mean. So in the first one, we're given a vertex 1, 3 and the point 2, 5. So let's start off by writing what vertex form looks like. It's y equals a times x minus h squared plus k. So from here, we are going to plug in y. So our vertex gives us h and k. Our point gives us x and y. So y here would be 5. A is what we're solving for. X would be 2. H would be 1. And k would be 3. So we have 5 equals 2 minus 1 is 1. 1 squared is 1. So we just have a plus 3. And then 5 minus 3 is 2. So a would be 2. So now all we have to do is write in what our equation would be. F of x equals 2 times x minus h, which is still 1, plus 3. All right, for example B, again, we're going to start off with our vertex form of our quadratic equation. We're going to plug in our y, which is negative 6. We're going to plug in our x, which is negative 2. Our h, which is negative 4, which gives us a plus 4 here. And then we're going to have k, which is negative 2. And we'll solve for a here. We have negative 6 equals a. Well, we've got negative 2 plus 4, so that's going to be 2 squared. And then we have 2 squared, which is 4. We add 2 to each side. We get negative 4 equals 4a. Divide by 4, and you get negative 1 equals a. So, since a is negative 1, we don't necessarily have to write the 1 part, right? The 1 is understood if we just put the negative in front of our x stuff. And so you're going to have x plus 4 squared minus 2. And then finally for part C, again we're going to start with the vertex form of our quadratic equation. Here y is 11, x is negative 1, h is 5, and k is negative 1. So we won't have a plus on the end here. We will actually have a minus. So let's see, x is negative 1, h is 5, k is negative 1. And then we solve it for a. So inside the parentheses, we're going to have negative 6. Negative 6 squared is 36. Add 1 to each side, you get 12. And then divide each side by 36, you get 12 over 36, which that can be reduced down to 1/3. And so we just write our quadratic equation in vertex form using what our a value is. 1/3 x minus 5 squared minus 1. So that's how you write your quadratic equation in vertex form if you're given the vertex and a point. All right, this concludes section 2.1. Coming up in section 2.2, we will talk about the quadratic equation in intercept form.